Let's start with our chapter 13, light. Reflection of light is our first concept. What is reflection of light? Definition: reflection of light is the process by which light bounces back into the same medium when it hits a surface. Some key terms that we must know at this stage. What is incident ray? It is the incoming light ray. Reflected ray is the light ray that bounces off. Normal and imaginary line drawn perpendicular to the surface at the point of incidence. Angle of incidence is I, angle between the incident ray and the normal. Angle of reflection, angle between the reflected ray and the normal. For example, if this is our plane surface, on this surface light hits. So when the light hits on the plane surface, it reflected back to another direction. This point is, we are calling it as 90-degree normal. This is our angle of incidence as it is making it with the surface. This is our angle of refraction as it is reflecting, bounces back to the surface. All right. So laws of reflection. The angle of incidence equals the angle of reflection. So angle I is equals to angle R. The incident ray, reflected ray and the normal all lie in the same plane. Types of reflection. We have regular specular reflection, occurs on smooth surface, example plane mirror. Parallel rays reflect parallel and there will be a clear image. Next is diffuse reflection, occurs on rough surface, example wall. Rays scattered in many directions, no clear image. Example, when light hits a plane mirror, it reflects such that the angles are equal, allowing us to see an image. Shiny metal reflects light strongly, a rough wall scatters it. Ray diagrams and ray angles. In optics, a normal is an imaginary line drawn at right angles 90 degree to the boundary between two materials. You can see here our angle of incidence, angle of refraction. This is the 90 degree, which is normal. This is our incident ray, this is our reflected ray, and this is our angle of reflection, and the surface is plane mirror. For reflection, the angle between the incoming ray and the normal is the angle of incidence, which is angle I. The angle between reflected ray and the normal is the angle of reflection, which means angle R. When drawing ray diagrams, the incident ray has an arrow pointing towards the surface. The reflected ray has an arrow pointing away from the surface. So if it is an incident ray, the arrow is pointing towards the surface. And if this is a reflected ray, so the arrows are pointing away from the surface. The law of reflection states that angle of incidence will always equals to angle of refraction. The law is used in devices such as mirrors, cameras, optical fibers, and periscopes. So angle of incidence is always equals to angle of reflection, which is our main point. Reflection in a plane mirror. When an object is placed in front of a flat plane mirror, its image has three properties. Learn these properties, important for the exam's perspective. The properties of that image will be same size as the object, same distance behind the mirror as the object is in front of it. The image is virtual, cannot be formed on a screen. To understand this, a ray diagram can be drawn. Ray leaves the object and strikes the mirror. Each ray reflects so that angle I is equals to angle R. To the eye, the reflected ray appears to come from behind the mirror. If these rays are traced back behind the mirror as dashed line, they meet at a position of the image. Because the rays only appear to come from that point and do not actually pass through it, the image is called as virtual. We have a diagram where we have top part and the middle connection, and then we have a bottom part. So, the explanation of this diagram is the top part, rays for direct view. Light rays travel from object directly into the eye. The light does not bounce off anything. Explanation: the object emits or reflects light. Light rays travel in straight line. These rays enter the eye. The brain interprets this as seeing the object directly. Key point: we only see an object if light from it enters our eyes. Then we have the middle connection, rotating arrows. These arrows mean the eye or object can change position, but the rule stays the same: light must reach the eye. They show that the direction of the viewing can change. Then we have a bottom part, rays of reflection. What is happening here? The object is not directly visible to the eye. Let's investigating reflection now. Aim: to investigate reflection of light from a plane mirror. Variables: independent variable angle of incidence is I, dependent variable angle of reflection is R, control variable distance between ray box and mirror, width of light beam, same type color wavelength of light, equipment, ray box to produce a narrow light beam, plane mirror reflecting surface, sheet of paper to mark rays, pencil and ruler to draw rays and normal, protector to measure angle. Now these equipments can make sense to you as you have already seen that how the light reflects on the plane surface with diagrams above. So method will be: place a sheet of paper on the bench, draw a straight line about 10 centimeter, use a protractor or set square to draw a line at 90 degree to this line. This is normal. Place the mirror along the first line with it reflecting face on the line. Shine the ray box so that beam hits the mirror at the point where the normal meets the mirror. Mark on the paper a point on the incident ray before it reaches the mirror, a point on the reflected ray a short distance from the mirror, and then remove the mirror and the ray box. Now use the ruler to join the incident point to the point on the mirror point to the reflected point. Measure the angle of incidence and angle of reflection using the protractor, and both can be measured from normal. Repeat the procedure for different angles of incidence. Your result will look like a table with angle of incidence, angle of reflection, for example, these angles. Analysis: if the experiment is done carefully, you should find that angle I is equals to or a congruent to angle R for each trial, confirming the law of reflection. Sources of error here and improvement in this experiment: if a normal is not drawn exactly at 90 degrees, angle will be wrong. Use a set square or accurate protractor. Poor quality mirrors may distort the reflection. Use a flat mirror without scratches. Marking the rays too thickly make angles reading less accurate. Use a sharp pencil and make the center of the beam. Use a protractor with fine scale markings for which accurate readings can be done. Safety: the ray box lamp can become hot. Avoid touching it and cool any burns under cold running water. Do not look directly into the bright beam. Keep liquids away from electrical equipment. Now let's discuss our second topic: refraction of light, angles and ray diagrams. For refraction, Angles are again measured from the normal. Angle of incidence, angle between the incident ray and the normal. Angle of refraction, angle between the refracted ray and the normal. Ray directions, incident ray arrow towards the boundary. Refracted ray arrows inside the second medium, leaving the boundary on the inside. So, what is refraction? Refraction happens when light passes from one transparent medium into another, for example, air into glass. You can see here this is incident ray when it touches the glass. How does it refracted? The angle with the normal and the angle of incidence. You can see clearly here this is medium 1, this is medium, this is the normal, this is glass in which the light is being refracted. At the boundary, light changes speed. Because of this, the result usually changes direction. Rules from less but optically dense to more optically dense. Example, air to glass. Light bends towards the normal. So when the light hits the glass, it bends. So when the light hits the glass, it bends. In any direction it can bend, but it needs to show some bending. Okay. From more optically dense to less optically dense, example glass to air, light bends away from the normal. If the air travels along the normal perpendicular to the boundary, it does not bend but it still changes speed. As you can see in the diagram here. So when the light hits the surface, it bends. Okay. All right. Next is when light enters and leaves glass block. When there are two boundaries, air to glass is the first refraction, then glass to air is the second refraction. The refracted ray from the first boundary becomes the incident ray at the second boundary, changes during refraction. Speed change, wavelength changes, frequency stays the same. Different frequencies correspond to different colors of light. Red, lower frequency, blue is higher. Since light does not change color, it refracts, its frequency remains the same. Let's discuss investigating of refraction method. Aim to investigate how light refracts through rectangular blocks, semicircular blocks, and prism. Variables, independent variable shape of block, dependent variable angle of refraction, control variables width of the light beam, same color wavelength of light. The equipment that we are going to use, ray box, perspex glass blocks, rectangular, semicircular, triangular prism, paper, ruler, pencil, and protector. So the method rectangular box example, place the rectangular block on paper and carefully trace around it. Remove the block and mark the outline as seen in the diagram. Replace the block in its outline. Shine a narrow beam of light from the ray box at one face of the block. So the mark point of incident ray before it hits the block, the point where it enters the block, the point where it leaves the block, and a point on the emerging ray a few centimeters away from the block. Now remove the block and ray box, draw straight lines joining incident mark, entry point, and exit, which is an emerging mark. At the entry and exit point, draw normal lines at 90 degrees to the block's face. Use the protector to measure angle of incidence and refraction for different trials. Repeat for other shapes, semicircular block and prism, and compare how the rays bend. Analysis by examining the different ray paths, you can see how angle of refraction varies with the angle of incidence and block shape. In the semicircular block, if light enters along the radius, it hits the curved surface along the normal and does not refract on entry, just on exit. Errors and improvement. Use a set square to ensure normals are accurate. Use a sharp pencil to improve precision. Use a protector with finer markings. Safety: ray box gets hot. Avoid touching the lamp directly. Avoid looking into the beam. Keep water and liquids away from the electrical equipment. Let's discuss about refractive index now. There are two useful ways to define and calculate the refractive index n of a material. Use the ratio of the speed, use the ratio of sines of angles. Refractive index is a number greater than 1, different for different material. Larger for more optically dense material. For example, diamond has 2.4 and glass has 1.5 refractive index. Unitless, it does not have any unit. Speed definition: n equals to speed of light in a vacuum divided by speed of light in a material. A higher refractive index means light travels more slowly in that material. Angle definition: Snell's law, n equals to sine I over sine R, where I is the angle of incidence in the less dense medium, usually air. R is the angle of refraction in denser medium. Conceptually, our formula will be n on the top here, and then sine I and sine R will be over each other. Sine I is equals to n when it goes to another side. Sine n sine R, it will multiply with it, and then it will be equals to sine I. Sine R is equals to, or if we need to calculate sine R, then this will go here and n will come there. So it will become sine R equals to sine I over n. These three formulas are important for you to remember. Let's do one worked example. Light enters the glass block. Refractive index is 1.53 of that block. With the angle of incidence, angle I 15 degree, and the angle of refraction R we need to calculate. N is given, which is refractive index 1.53, I 15. Use the formula. Place the value in place of sine I, sine 15 in place of N. Refractive index 1.53, as we need to calculate the R, we have exchanged its places, so it becomes sine R equals to sine I over N. So after replacing the value, we will get R equals to 9.7 degree, which we rounded off to 10 degree. Remember that we never treat sine I over sine R as I over R. You must keep sine functions. Alright, now let's discuss about total internal reflection, TIR. Total internal reflection happens at the boundary between two materials when light travels from a more optically dense medium to a less optically dense medium. The angle of incidence is greater than certain angle called as critical angle. All the light is reflected back into the denser medium, none refracts out. At first, for smaller angles of incidence, most of the light is refracted out and a weak reflected ray remains in the denser medium. This is just internal reflection, not total. As the incidence of rays increases, the angle of refraction grows until it reaches 90 degree when the refracted ray travels along the boundary. At this point, the angle of incidence is critical angle C. So if angle of incidence is greater than critical angle, refraction no longer occurs. Instead, all of the light is reflected back inside. So this is total internal reflection. Conditions for total internal reflection is light must go from denser to less denser medium and angle of incidence must be greater than the critical angle. TIR produce brighter, more intense reflected beams than normal reflection. Refractive index and critical index angle for a medium of refractive index n will be equals to sine c equals to 1 over n, or you can replace the value of n with sine c in case you need to calculate n. So higher n means smaller critical angle c. Material with high refractive index like diamond more easily produce TIR. Now let's see one worked example. Opal N is 1.5 and in diamond it is 2.4. When we use the angle of critical angle here formula, we get it as 42, and for diamond we get it 25. So material with high refractive index like diamond are more easily to produce TIR. So diamond can easily produce more TIR. Diamond has a smaller critical angle, so rays inside are totally internally reflected over a larger range of angles and it appears to sparkle more because the angle of critical angle for diamond is smaller as compared to opal. That's why diamond shines more. Okay, uses of total internal reflection. Number one, optical. It can use in optical fibers. Thin, flexible glass or plastic fibers carry light signals. Light entering from fiber is totally internally reflected, repeatedly traveling along the fiber. Uses it can use as medical endoscopes, viewing the inside of the body, telecommunication, internet, landline phone, cable, TV. In telecommunications, electrical signals are converted to pulses of light. These pulses travel close to speed of light along fibers. As the receiver, they are converted back to electrical signals and then to sound or data. Now let's talk about prism in instruments. Right angle prism use TIR to reflect light inside devices such as periscope, binoculars, telescopes, some cameras and safety reflectors. In periscope, light entering the top prism is totally internally reflected downwards to the lower prism, which reflects it towards the viewer's eye. Ray diagram for lenses, key terms, principal axis, a straight line passing through the center of the lens. Principal focus is also called as focal point, where rays parallel to the principal axis converge or appear to diverge from after passing through the lens. Focal length, distance from the center of the lens to the principal focus. Now we have two types of lenses, converging yani convex lenses, thicker in the middle, makes parallel rays converge to the point, has a real focal point. Another is diverging, also called as concave lens, thinner in the middle, makes parallel rays spread out, makes appear rays appears to come from a focal point on the same side or as the light source. The more curved converging lens, the shorter the focal length. Now let's talk about real and virtual images. Real image formed when rays of light physically meet, converge, can be projected onto the screen, always inverted compared to the object. Example image on a camera screen. Let's talk about virtual image formed when rays do not actually meet but appear to come from a point. Cannot be projected on a screen. Always upright. Example image in a plane mirror magnifying glass image. Converging lens, real images, rules for drawing ray diagrams. Converging lens, we have some diagrams here for you so that you can practice. A ray through the optical center passes straight through without bending. So in the middle, without bending, ray 1 is bending and ray 2 is also bending. A ray parallel to the principal axis refracts through the lens and passes through the focal point on the far side. Here from an object you can see multiple rays. As soon as they hit the lens, they all form an image location behind and how the eye can see it at different locations. So a ray passing through focal point on the near side emerges parallel to the principal axis. Depending on where the object is placed, for example, beyond object beyond 2f, image formed between f and 2f. On the opposite side, real inverted smaller diminish. Object at 2f, image form at 2f, real inverted same size. Object between f and 2f, image form beyond 2f, real inverted magnified. Now let's see some worked example. Draw a ray diagram showing a diminished real image using a converging lens. So a diagram can be like this. Draw principal axis and lens. Mark focal points F on both sides. Place object beyond 2F on the left. Draw a ray from top of the object through the optical center. Draw a ray from top of the object parallel to the axis, then through focal point on the right. Where two rays meet at the right is the top of the image. Draw the image down to the axis. Label object, image, and focal point. The final image will be real, inverted, and smaller than the object. Similarly, in converging lens, where we have virtual image like in magnifying glass in an object is placed closer to the lens than the focal length, a converging lens produces a virtual upright magnified image. The image appears on the same side of the object. This is the principle of a magnifying glass. Again, you have some images to practice. Regardless of where the object is placed, beyond F or closer than F, the image is always virtual, upright, diminished, on the same side as the object. Ray behavior. A ray through the optical center passes straight through. A ray parallel to the axis refracts as it came from the focal point on the same side. When these refracted rays are extended backwards, they appear to come from a point, the virtual image. You are not usually required to draw diverging lens diagrams perfectly in exam, but you must know the image is always virtual, upright, and smaller. Correcting sight. Lenses are used in glasses and contact lenses to correct vision problems. Long sightedness, hyperopia, eye lens is not curved enough or the eyeball is too short. Light from near object it focus behind the retina, result difficult seeing nearby objects clearly. Correction, use a converging convex lens in front of the eye. This lens makes incoming ray begin to converge before they enter the eye. The eye lens then brings them to focus on the retina, forming a clear image. Similarly, we have short sightedness, myopia, eye lens is too curved or the eyeball is too long. Light from distant object is focused in front of the retina, result difficult seeing distant object clearly. Correction, use a diverging concave lens in front of the eye. This lens spread the rays out slightly before they enter the eye. The eye lens then focuses them further back on the retina. Dispersion of light. As you can see, when the white light enters the prism, it disperses into different colors: red, orange, yellow, green, blue, indigo, violet. When white light passes through a glass prism, it separates into a spectrum of colors. This is called as dispersion. When light contains all colors of the visible spectrum, white light contains all colors of the visible spectrum. Each color has a slightly different wavelength and thus refracts by a slightly different amount. Violet, shorter wavelength, higher frequency, is refracted the most. Red, longer wavelength, lower frequency, is refracted least. This separation produces familiar rainbow colors like red, orange, yellow, green, blue, indigo, and violet. A handy memory set Richard of York gave battle in vain. Like this, you can learn their wavelengths. Roy G. Biv. Visible light is the only part of the electromagnetic spectrum that human eyes can detect, but many animals can see beyond this. For example, UV or infrared red lights. Monochromatic lights. What is monochromatic light? A monochromatic light source emits only one frequency, which is one color. An example is a laser. It produces a narrow beam of single color light. Example, green laser. With this, we have finished our chapter. See you in our next chapter.